Explain your answers. The assignment of students to locker numbers. The assignment of zip codes to residences. All right. So it's basically like for the first one, if I go to the main office and I give the name of the student, can they tell me the locker number of that student? Right? Is there one locker number associated with each student? All right. Or actually, this one might be the other way around. The assignment of students to locker numbers. So if I have a locker number, does that correspond to a specific student? Honestly, either way, it seems to make sense. So we would say that this is a function. Yes, a student would correspond to one locker. Now, there are other ways to interpret this. So, like I'm just going under the assumption that we're talking about the lockers that you see out in the hall. Right? I'm not including, like, I don't know if gym lockers are still a thing, but like I'm not going down that road. But, like that's a possibility. So you could say no, because if I identify the student, then are we talking about the locker for academics? Are we talking about the gym locker? Or maybe they have a storage locker for art supplies? Like, who knows, but I'm making an assumption here. And that's one of the reasons why, I've said this a few days in a row now, this topic doesn't really lend itself to a unit test. It's more like a project-y sort of topic, because you have that gray area where you can make a judgment. Like I'll say, yes, it's a function, and you'll say, well, no, because what if you didn't consider all these other possibilities? I'll be like, yep, you're absolutely right. All right, assignment of zip codes to residences. All right, so that's saying that if I know the residence, then I would automatically know the zip code, or I could automatically know the zip code. Now, that's another tricky one. How do we define a residence? A residence could be an address, all right? In most cases, that's what it represents. But how specific is that address? I would hope everything except for the zip code, all right? So if I say that you're living on 27 Maple Street in White Plains, I'm going with White Plains only because there's multiple zip codes that make up White Plains. All right, I'm not as familiar with Katona and Vista and South Salem. I mean, I'm familiar enough with the names. Obviously, I just said them, but Lewisboro and all that. But I don't know enough about zip codes in this area to make a definitive statement. Like, for example, I have a White Plains address, but I don't have a White Plains zip code. All right. I got not yelled at, but like spoken to like I was an imbecile, which in my mind is like getting yelled at, by a postal worker at the post office on Fisher Avenue in North White Plains, because I went there to pick up a package. Like, the little slip that came to my door said, "Go to the Fisher Avenue post office." Well, apparently, the post office in White Plains, not North White Plains, is also on Fisher Avenue. I just assumed it was the one that was closest to me. They're like, no, it's the other one. I was like, how is I supposed to know that? It says it right there. And I'm like, so does the sign outside. What do you mean it says it right there? So that was a fun interaction. I eventually got the package. It was nice. It was a nice hat. But anyway, just because you know the residence doesn't mean you necessarily know the zip code. All right. Strong chance you do. This one could go either way. All right. So I might say no, multiple addresses. It is possible that you could have a similar address but in a different zip code. But the most likely answer is yes, you could have, in most cases, if you identify house number, street, town, you're probably going to have a corresponding zip code that makes sense. All right, so that's the one I would lean towards. not my crazy post office experience. All right. So I'll say yes if you know specific house number, road, town, you would be able to identify the zip code. Another gray area type question. I mean, it's very tricky. All right, but the numbers questions are the ones where you're like, oh, okay, finally, there's something that makes sense. Determine whether each relation is a function and explain your answer. You're just looking to see if any x corresponds to multiple y's. All right, 4 gives a 5, but it also gives a 6. So this is not a function. Four maps to multiple y value, or well, outputs, I'll say, because they didn't designate. Just the word on terminology here. I use the term map in this instance. Mapping is a visual representation of corresponding. All right, so when I say one thing corresponds to another, I could say it also maps. One thing maps to another. It's kind of a nice, shorter, one-syllable way of writing it. All right, then the domain and range, that should be easy enough because all I'm doing is indicating the unique input variable or values of the input variable and the unique values of the output variable. So -8, 1, 3, and 4. And then 5, 6, 7, 8. All right, number 3. Again, just looking to see if any x maps to more than one y. I see here that I have a 4 that corresponds to a 5, but a 4 also corresponds to a 7. So visually, I'd say 4 maps to a 5, 4 maps to a 7. All right, so not a function. Actually, the same explanation. 4 maps to more than one or to multiple outputs. All right. Now, whether or not, oh, I'm sorry, we already took care of the function. The domain and range, squiggly bracket, unique x values, -2, 3, and 4. For the range, it looks like I have, oh wait, is there a -2? Oh, I got a little cross-eyed there. I saw 2 -2s next to each other. That's why I got to go with my highlighter approach, because got to keep this stuff straight here. So we have -2, 5, and 7. All right. So let me see. So I don't need to highlight both of them. -2, 5, and 7 are the unique range values. For the domain, it's -2, 3, and 4. Okay, good. Do it too quick, you kind of lose track of things sometimes. All right. The last couple of questions, not too bad, because when it comes to identifying whether or not a relation is a function graphically, it's a matter of applying the vertical line test. So I'd slide or drag my vertical line through the graph and see if it ever intersects with a point more than once. It does right here. So this is not a function. And coincidentally, I could actually, because this happens to be at an x value of 4, I actually could use the exact same explanation. It's not a function because 4 maps to multiple outputs, but the same thing happens for 6. Although I could also say not a function because it fails the vertical line test. VLT, we can use as an abbreviation for the vertical line test. All right. And the last one, we would also apply a vertical line test. Same deal. Drag a vertical line across your graph. All right, and see if it ever intersects more than once. All right, it never does. It makes it all the way through without intersecting more than once. So this is a function. A punction? I don't even know what I was going to write there. Function passes the vertical line test. All right. So I use a vertical line and I drag it through because I have the option to do that. But, you know, just use the edge of a piece of paper, a ruler, a pencil, and just kind of slide it across if you need the visual. Some folks don't, and that's perfectly fine. We do need to state the domain and range. All right. So in the case of the points, that's nice and easy because just like yesterday, I'm going to bring that in a little bit. We just need to identify any x value that corresponds with points on the graph. That would be 2, 4, and 6. For the range, we want to identify any y values that fall on the graph. All right, so that would be 1, 2, 3, 5. Oh, I missed a 4. 3, 4, 5, 6, and 7. But again, as we know, we're not going to say 3 through 7. We're not going to use interval notation here because these are specific points. They're not connected. So 3, 4, 5, 6, 7, as annoying as that seems. All right? It's annoying, it's tedious, but you got to do it. All right. Now, for the last one, this is a graph that extends forever in each direction, going down forever, going up forever, going left forever, and going right forever. So the domain here would be something that we'd state in interval notation. It goes negative infinity to infinity, and the range also goes negative infinity to infinity. I came up with this, animation is a strong word, because it's definitely not that. I'm going to show you, I think it's next week, how to use scratch coding to make, if you don't already know this, to make animations, because that's function related. And so it ties in nicely with what we're going to do. It's actually part of the project for the unit, so it's kind of cool. Technological. It's coding, but it's not going to involve the Sphero robots. I tried to do it with the robots. It was just too clunky. I'm sure it's actually something that's probably not as difficult as I think it is. It's just maybe I don't know how to do it. But I'll show you how to do some animations. But for now, all I did was I manually did something on a website and I just screen recorded it. So I have this graph. You can see my little mouse moving there. So I took this U-shaped curve. Now, what I wanted to show is how this looks from the perspective of the x-axis and how it would look from the perspective of the y-axis. Now, I had this idea that what I would do is draw a graph up on this thing here and then just kind of maneuver it, flip it on its side, and we'd look at it long ways and then look at it a different ways. Obviously, that's problematic on several different levels. One, it's mounted to the ceiling, kind of, but also it's a shield. It's there for a reason. So I did the next best thing. I used a three-dimensional grapher and it's on GeoGebra. I can show you that in a minute. But I made a curve here, and it looks like, if we look at this carefully, that this graph goes from -2 in terms of x to +2 in terms of x. And then the lowest y value it has is 0, and the highest y value it has is 4. So what I did was I just manipulated it so that we looked at it from the perspective of the x-axis. So I just kind of folded it down. And this is equivalent to if you had like sort of like a 3D printer, and you drew that graph on paper, but with a little bit of elevation, and then you just kind of took a little side view. All I did was I took that paper, which is aligned vertically, and folded or turned it away from me. I look at this and I say, all right, this is the x-axis, all right, but it's really a number line associated with the x-axis. I look at what part of this graph is covered. What part of this number line is covered by the graph? -2 to 2, which is what I thought the domain was. All right, so all the domain is what part of a two-dimensional graph is covered on the x number line, or covers the x number line. So then what I did was I rotated it and looked at it from the perspective of the y-axis and pushed it down onto its side. A little shaky hand, but you get there eventually. And so you can see the part of the y-axis number line that's covered by the graph is 0 to 4. Right? So that gives you the range. So there's a number line associated with the x-axis, and there's a number line associated with the y-axis. All right. So in case anybody's wondering, it's part of a program called GeoGebra. Let's see, where do I have it here? 3D. So it's here. It's a pretty funky expression that you have to put in, but it's something that can be maneuvered. There's a 3D grapher if you want to explore it. It's geogebra.org/3D. You can just start, honestly, it can be kind of addictive. You start sort of typing things in, and you see what comes up. They have an AR app that you can use. It's sort of cool. Right, but that's like fun fact of the day territory, but it's something. I just wanted to take a second and show you what this would look like.
So I'm just wondering, like, for the vertical line test, it's kind of, we have to think about it in the context that if it were like a bar graph, like there could only be one value on the y-axis. On the x-axis. So there can only be there can only be one value, because you can't have like two bar graphs on the same
Right, unless it's for two different variables. Yeah. So we're talking about a single variable. If I tell you the number of people that have red hair, and then you say 2, and then you say also 4, it's like, well, which one is it? That very good analogy. All right. So what we're going to do now is move on to function notation. All right. Now, function notation is very. Honestly, this is the weird unit. So everything I'm going to talk about, I'm going to introduce by saying, well, this is weird. So you see f parentheses x. This is known as f of x. This stands for the function of x. All right. So what we say as a general rule for functions y equals f of x, which means, well, it's a direct relationship, as in, like, you can substitute. F of x and y are interchangeable. But it also means that y is a function of x. All right. So this notation tells us, and it's really important notation. It's the kind of thing where you look at it and say, there's no way this could be important. And then years later, you'd say, how did I ever think that this wasn't important? All right. So, there's an element of belief here now, but that's really how it goes. All right. What this tells us is that, first off, the expression that we're dealing with is a function. It's been stated that what you're working with is a function. No need to test it by applying the vertical line test or evaluating the context. All right, the last few pages, all that stuff we did, kind of irrelevant, because if they say f of x, they're telling you what you're working with, the equation you're working with is a function. All right, so what this would be read as is y equals 3x minus 1, where y is a function of x. Therefore, if y is a function of x, we would say f of x is equal to 3x plus 1. All right, so that whole transition is actually happening here. So instead of them saying all of that stuff, they just say f of x is equal to 3x plus 1, and they hope that you know what they mean. All right. So for most people, that just means that all you'd have to do is type in y equals 3x plus 1. If you wanted to create a graph, let me get rid of all this stuff in one shot here. New blank graph. So I could type in y equals 3x plus 1. Linear equation, right? I could also type in f of x. So f parentheses x equals 3x plus 1. You'll notice how the graphs are exactly the same. And that's because y and f of x are thought of as the same thing. All right? The only difference is we're making the statement that y is a function of x. Now the thing you got to be careful about, among other things, is that it's not a product. The f parentheses x is notation. That's saying we have a function of x. It's a verbal term, right? It's not a product, right? They're using parentheses the way you would if you were making a description in an essay. So you write a sentence, and then you open a set of parentheses after that, and you put a little clarifying statement in the parentheses. You'd say, I'm going to wear shoes this morning, in parentheses, the red ones, something like that. Those parentheses don't mean multiplication, right? Those are the same kind of parentheses that we're using here. It's creating a descriptor. So we're saying function f where the relevant variable is x. So what that means is that we're eventually going to be working with situations where there's going to be more than one variable in the equation. And only one of them is going to be the one that we care about as the input. All right. Now, in terms of evaluating a function, that's actually pretty easy. It's a set of processes, and this is why Desmos is such a useful resource, like incredibly useful resource, right? So if I say f of x is equal to 3x minus 5, I could just type that in. They say find f of 4, all right? So I would type in f parentheses 4. And it tells me what the result is. 7. Done. All right. Now, it doesn't tell us what that means, which is kind of important. All right. So what this means, f of 4, the interpretation, aside from this being the weird unit, it's also the unit about interpretations, which many might find weird anyway. All right. F of 4 means given function of f of x, given a function y equals f of x, let x equal 4. All right. So this shorthand notation is replacing all of that stuff. All right. So instead of saying given a function y equals f of x, where x is equal to 4, or let x equals 4, they're saying just write f of 4. Everybody will know what you mean. Right? Which means that we have to learn the vocabulary in order to know what everybody else is talking about when they say stuff like this. All right. So in this case, we have some function y equals f of x, which in turn equals 3x minus 5. They're saying let the x value equal 4. All right. So y is a function of x. Just notation. They're saying let the x value be equal to 4. So this part is notation. We do nothing with it. All right, we just leave that alone. The other part is where we actually do the evaluation. All right, evaluate, value. All right, it's kind of weird. Like you use evaluate all the time in real life. I mean, maybe you don't think of the word all the time, but you're evaluating stuff. When you're evaluating stuff, most of the time you're assigning a number to that thing you're evaluating. I mean, sometimes that classification is good or bad, but good is usually considered some positive value, bad is considered some negative value. It still has a numerical component to it. All right, but if I take 3 times 4, that gives me a 12, minus the 5, that's going to get me the 7. I now just found the value of the function when x is equal to 4. Now specifically, since this whole thing was equal to y equals f of 4, this tells me that the y value when x is equal to 4 is 7. This part nobody ever likes, because what this does is it begs the question of why'd you make this so complicated? All right. Because if I tell you that the y value is 7 when the x value is 4, isn't that the same as saying that the coordinates are 4, 7? And isn't that the same as saying, well, couldn't I have just found the coordinates at 4 on the graph? And the answer is yes. So if you go to 4 on the graph, you'll get a 7. The y value associated with this x value of 4 is the evaluated number. All right. So after all that, you're like, oh, we've been doing this all along. You're just attaching this crazy notation to it. To which I reply, I didn't make up the rules. I'm just a relayer of bad news. Yeah. No, it is what it is. It's the language of all the math that we're going to be learning going forward. So we got to get it down at some point. But a very, very simple way of understanding this would be to say, if I have something like f of 4 means find the y value when the x value is 4. All right, so we got the mathy explanation on the right, and we have the, all right, let's cut to the chase, let's get down to business, how do we do this, explanation on the left. All right. Then immediately what do? I switch it over to H and B's. That messes people up pretty significantly. That probably happens a little early on in the process. So let's make that H of X, F of X. So I'm going to change this example just because it gets a little too confusing too quickly. I'd rather wait to make it too confusing. Nah, honestly, it should never be confusing. And honestly, regardless of the letters that are used, the notation, the format of the notation always means the same thing. All right, so h of b, 3b squared minus 2b plus 1, blah, 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 that all is interpreted the same way as f of x equals 3x squared and so on. All right. But honestly, it's still a little too early in the process to jump to an example where we start messing around with the letters. So we're just going to make that change. So find the value of f of x when x is equal to -3. All right, so what that's saying, essentially, so this means find y equals f of -3. Because they're saying use the x value of -3. What that's telling us to do is substitute in a -3 for x. All right, it's essentially saying, again, find the y value when the x value is -3. So if I'm making a substitution, I would do it if I'm doing it by hand. So y equals f of x would be equal to 3x squared minus 2x plus 1. I'm really looking for y equals f of -3. The f of -3 is just the notation part of it. The real action happens on the right-hand side, where I replace all the x's with a -3. That's how you evaluate an expression. If I wanted to find the coordinates for y, if I knew what x was, I'd replace all the x's with the number. Question?
If you understand it, you have to change to the fx?
The changing of the f of x is the whole point of everything. So you would have to show that every time.
Oh.
Yeah.
I said that we had to change because it was less confusing.
No, that's the explanation so that you understand what the notation means. But the whole point of this is to understand the notation. All right. Yeah, I was just trying to relate it back to what you had seen before. But yeah, the whole point of this unit is to transition into the new form of writing this stuff. All right. So f of x is equal to 3x squared minus 2x plus 1. Using Desmos, I could type in f of -3, and I would get a result of 34. Now that's what I would get if I clean this up a little bit. All right, so I'd be looking at 3 times 3 squared. So 3 squared is not. I'm sorry, -3 squared is still 9. Times 3 is 27. Plus 6 plus 1 gives you a result of 34. So either way you're going to get it. Both ways rely on the notation. All right. A good way to check your work, and again, if it's a multiple choice question on a test, different story. Do it like, how would I know? But for a free response question, you'd have to be prepared for this. But like I said, this is a project unit, not a test unit. On the Regents, a different story. They want free response questions to be done a certain way. You don't have a choice. All right, assuming you want to get credit. All right. So the next one, that's probably a little much at this point. But so we'll skip that one. Let's do number 4. And then that should set you up for pages 5, 6, and 7. All right. So this one says, given f of x is equal to negative 4x minus 10, if f of n is equal to 14, what is the value of n? All right. So this is going the other way. All right. So we have y is equal to f of x, which is equal to negative 4x minus 10. They're saying that f of n is equal to 14 somehow. All right? That y equals f of n is telling us to replace each of the x values in our given function with an n. And that should result in a value of 14. All right? So that's showing that these two numbers, so f of n is equal to 14, we have the relationship in here. Just along the way, we showed that that's also equivalent to negative 4n minus 10. All right? Now this piece is the notation. That's just the recipe, but it's this piece that we have to solve. So we have a linear equation. Negative 4n minus 10 is equal to 14. So we go ahead and solve that, and once we do that, we'll know the n value. So I'd add 10 to both sides. So negative 4n is equal to 24. Divide by the negative 4. And you get n is equal to negative 6. All right. But very quickly before we end, let me just show you the Desmos approach. So the original function was negative 4x minus 10. In Desmos, you could type in f of n. Create a slider, and just keep moving that slider until you get the desired number. Now, I had an idea that it was around negative 6, but even if I didn't, I would see that it was trending in that direction. You know, as I got more and more negative for n, the values got more and more positive for f of n. So once I get to negative 6, I get the desired value of 14, and there we go. All right, so the Desmos approach is really beneficial for this topic. So we want to make sure that we can keep using that. All right. So there we go.